Hello and welcome to Chapter 15. Starting a new chapter, so we only have two chapters left, Chapter 15, Chapter 16, and we're finished with Calc 3, so we're pretty much halfway there. And today what we're going to do is we're going to talk about finding the double integral over a rectangle, and basically the idea is going to come from finding our integral using Riemann-Sums back from Calculus 1. So today we're just going to talk about that same idea. So it's not going to be a long day today. So here we have a curve. Right? Our curve, here we have a curve. And what we want to do is we want to find the area underneath that curve. And so when we started off in Calc 1, we were like, instead of actually taking the integral of it, what we did was we took a bunch of little rectangles, and we would either put them at the right hand and would make our Riemann sum using the right hand rule, or we would do the left hand rule where we would try to find the area underneath that curve of Riemann sums using the left hand rule. And then we did the trapezoidal rule, and we also did trapezoidal rule. It's pretty nice. And then we did the midpoint rule, where we would take the value at the midpoint and try to estimate, hey, is this the area underneath our curve? Well, we're going to start off with the same type of idea in Calc 3 when we're trying to find the volume underneath the surface. Right? So now that we're in three-dimensional space, our function is going to give us a surface, and what we want to do is we want to find the volume underneath the surface. Right? And so it's not really complicated because we're trying to find volume. What I want you to do is look at look down here at this example. So here we have a surface. Now instead of finding using rectangles, now we're going to use prisms underneath our surface. And instead of finding the area, now we need to find the volume of each prism. And so in order to find the volume of each prism, what you need is length times width times height, right? And that's how we find the volume of any prism. Well, in this case, all right, just like how we found area for each of these little rectangles, we're finding volume for each of our little prisms that we're going to make underneath our underneath our surface. And so in order to do this, we're going to multiply the area times the height. And so here's like our little Riemann sum. We're going to keep adding the height times the area of each of each little prism by the x width and the y height. And then we're going to, x width and the y length, or, the x length and the y width. It doesn't matter, right? And so that's how we're going to use our Riemann sums. I haven't erased that. But using prism. So this is what this formula means, right? To find our area, it's just going to be our delta x times our delta y. We're going to multiply the width of our x's times the length of our y's. That's going to give us the area. And then when we multiply by the height, that's going to give us the actual volume of our prism underneath our surface. And so that's basically the idea of what we're going to do today. Alright, let's go ahead and now just do an example. Well, I guess not an example yet. Alright, so to find the double integral, again, it's just going to be to find the double integral of our functions. What that's going to be just the sum of all of the prisms times I'll say the sum, it's just the sum of all of our prisms, and how we can, the sum of all the volumes of our prisms. So this is what this formula says right here. So as we go from starting at M and N are going to be how many subintervals that we have to make all of our prisms, and we're just going to start at 1 and go all the way to M and N. And again, this is to find the volume of each singular prism. And so we're just going to add all these prisms up underneath our surface, and that's going to give us the volume. Alright? A function f is called integral if the limit exists. If f is bounded and f is continuous there, except on a finite number of smooth curves, and f is integrable over R. And a volume can be written as a double integral. And so hopefully none of that is going to be confusing. So now we're just going to go ahead and do a few examples, and that's going to be it for today. So again, today's going to be really short. So again, the sum is going to be called a double Riemann sum and is used as an approximation to the value of the double integral. So again, we're approximating, we're not actually finding the volume underneath our surface. So we're going to estimate, so for number 4, what we want to do, so our first example, it's example 1, but it comes from question 4 in the book. Estimate the volume of the solid that lies below the surface. Z equals 1 plus x squared plus 3y, and above the rectangle. Alright, and so we have 1, 2, and 0, 3. And we'll use a Riemann sum with m equals n equals 2, and choose the sample points to be the lower left corners. Alright, so let's go ahead and draw what this would look like. Right? It's always a good idea if we're going to do this by hand to draw what the Riemann sum is going to look like. So we're told that for the x, we're going to go from 1 to 2. So there's 1, there's 2. And for y, we're going from 0 to 3. And so here's our shape. So here's the rectangle that we're going to use to find the area. To find the volume underneath our surface. Right? And our surface is defined by z equals 1 plus x squared plus 3y. And how many, I'm going to break it up into 2 subintervals for each m and n, m the x direction and the y direction. So here's breaking it up into 2 subintervals in the x direction, so that's going to be 1.5. And then here's breaking it up in the y direction, and again, that's also going to be 1.5. So now I have 2 subintervals in both directions. And choose the sample points to be the lower left corners. Alright, so that means my sample points, I need to change, I'll put the blue, are going to be, so for each subrectangle, I'm going to take that value. Hear me express that. So for this first subrectangle, the value that I'm going to take to find my height is going to be from the lower left corner, and that's going to be from each spot, from each rectangle. So that rectangle is going to be found by that lower left corner. This rectangle is going to be found by this lower left corner, and this rectangle right here is going to be found at that lower left corner. All right, and it will give you pretty much where it goes. It could say upper right corner, and in the case it'd be there for all subrectangles, upper left corner, or lower right corner. So now let's go ahead and we're going to use the lower left corners to find the volume. Right? And so we want to find the volume. So the volume is equal to, again, I'm just going to write the notation. So you could skip ahead in the video till I finish writing this notation. It's just me writing everything out. And this is approximately, and then I'm just going to write the sums. That is the ugliest summation symbol. Let me zoom in so I can write a little bit better. And now we're going to go ahead and substitute in for what each of those mean. And so what we're going to do is we're going to take the height at 1, 0. So we're just going to plug into the function to determine the height times our delta A plus our next value, which is going to be f of 1 and I could say 1.5, right, times delta A plus f of 1.5 times not times, f of 1.50 times delta A, and plus f of 1.5 times delta A. Alright, so now let's determine what our delta A is. And if I look here, delta A is, again, just the difference of x times the difference of my y's. And so they're all going to have those same distances. So our distance for the x right here is going to be 1/2. Our distance for the y is going to be 1.5 or 1.5. I'll write that as a fraction because it's easier. So that means that my delta A is going to be 3/4. So each of these subrectangles has an area of 3/4. And now, in order to find the volume, we're going to extend that by the height. And so now let's go ahead and find the volume. Alright, so we have f of 1, 0. So we're going to plug this back into z. So when I do that, I get 1 plus 1 is 2, and then times 3 times 0 is going to be 0. So the height is going to be 2 times my delta A, which again we found over here by saying that's 3/4. So it's going to be 2 times 3/4. And so now again I'm just plugging back into the function. So again, plug in 1 and 1.5 into z, and we get through that, we go ahead and get 13/2 times 3/4. And again, just like you did, hopefully you did this in Calc 1, instead of having to write the 3/4 over and over and over again, you could pull out the 3/4 to the front, just so that you don't have to write as much, because again, these all have delta A in them, so you can pull out the delta A. And I'll do that the next example, so you don't have to continuously see me writing the delta A, delta A, delta A. Alright, so let's plug in f of 1.5 and 0. Alright, when we plug that in, we get 13/4. And then let's plug in, don't forget to times the delta A. And then plus, and then finally plug in 1.5, 1.5, and we're going to get 31/4. 31/4, not 31.4. Times 3/4. Alright, and so we go ahead and do all the math there. We get 117/8, or 14.625. And there's our answer.